Hey guys, this is Professor Janacek. I want to talk about limits. Let's start by letting f be a function defined for all x near some value a, except possibly at that value a. Now, if f of x gets close to some number L, as x gets close to that value a, then we say the limit of f of x as x approaches a is equal to L. The notation of that is right here. We can read this one of two ways. We could say the limit as f of x, the limit of f of x as x approaches a is equal to L, or we can say the limit as x approaches a of f of x is equal to L. Either way, as x is getting close to a, our function is getting close to L. Now this is an informal definition. But it's a nice way of thinking about it. Let's take a look at an example. Suppose we have this function s of t equal to negative 16t squared plus 96t, and v of t is s of t2 minus s of t1 over t2 minus t1. You'll notice that this does have the look of the slope, and that's exactly what it is. In this case, t is time in seconds, s is position in feet, and v is our average velocity in feet per second, which we could also denote as v sub ave. All right, so now let's do some calculations. If we put into our v function t equal to 1 and t1 equal to 1 and t2 equal to 3, what do we get for v? Well, in that case, let's see. Evaluate, we're going to evaluate it into this one, and then of course use that to evaluate it here. Doing all those calculations, we end up with 32. So what I'd like you to do now is take a moment and do the rest of these calculations. Pause if you need to. So simply take t1 and t2, figure out what s of t1 and s of t2 are, and then figure out what v is from that. Take a moment, give that a shot, see what you come up with. Alright, so hopefully these are the same values that you got. And so let's see what's going on here. So first off, we are definitely looking at the slope in this situation. We're specifically looking at t2 values. Notice our t2 values. All of these are getting significantly closer to our t1 value. So t2 is approaching t1. Then we're looking at the slope. So the first one, we looked at the slope between t1 and some t2 value, and then t1 and some other t2 value that was a little closer, and then it was the slope between t1 and another t2 that was even closer. And so we keep getting closer and closer with our t2 value and finding that slope. I do want to point out that these guys are referred to as secant lines. And we are, of course, looking at the slope of each of these secant lines. And you'll notice that we can actually use this to figure out what is the slope at just a single spot. So that's what we're trying to figure out, is what is that v at an instant. Well, it turns out that if I were to take the limit, as in this case T2 is approaching T1, of the slope of those secant lines, I'll write that as M sub SEC, what we end up with is the slope of our tangent line. So there's our tangent line, the slope of that. In general terms, not just looking at slopes, in general terms, that's saying that the instantaneous velocity is the limit of the average velocity. In this particular instance, our t is approaching 1. I have that written as the limit as t approaches 1 of, again, that average velocity is also the slope formula. And looking at this, you see that it looks as if, well, here we go, we keep getting close to something that looks like 64. So in this case, our limit is 64, and that's the idea. So as t, our time, approaches 1, our function, v, the velocity, approaches 64. Don't forget the units on this. This one is seconds. Our velocity is feet per second. Hope that's clear. Enjoy.